So I posted, I forgot to hit record the last time we met. So I took my other section and kind of the material that we covered during that class. I took the video from that section and put it up on the YouTube page. I also yesterday put up kind of the next Excel assignment. So after today, you'll be able to kind of work through that first portion of it. So it's kind of broken down into 3 sections. We'll really only be able to work on that first section after today. The rest of it will probably be stuff that we cover next week. So after next week, you'll probably be able to finish the whole assignment. But for now, right, you'll only be able to kind of work in that first third. The Connect, you should be able to make pretty far through the Connect homework. Some of the later questions will be some of the stuff we cover next week, but I want to get those up there so you can start working on it kind of as we progress, because kind of like that Excel assignment, it's broken down into 3 kind of topics, right? By the time we cover the last one, going back to the very first one will seem like it was a kind of, far off in the distance, right? I'll kind of might not remember it quite as well. So I would start trying to kind of chip away at these. And I'll try to mention about how far you can make it after kind of every class. Like I said, after today, a third of the way through Excel, and I would say somewhere roughly around a half of the Connect problems we should have kind of covered. Okay. Any other questions from me before we kind of jump into things today? Okay, so let's get going here. I'll try to take a little bit more time on some of this earlier stuff. Some of the stuff we covered at the end of class today, I'll probably go a little bit quicker through it because it's not quite as important. It's kind of setting us up for what we're going to talk about next week. So we left off kind of thinking about this normal distribution, right? And so I know that we had worked through some examples where we're looking for the probability that we see a certain value or lower, right? So we'll kind of do the opposite today, which is the probability to see a certain value or greater. And we took a look at how we did this in Excel, but we'll kind of see how it plays out if we work through it by hand. So hopefully this kind of also gives us a little bit of a refresher as to what we were doing before fall break. Right? Because a little bit of time off. We were talking about like rainfall and how that follows a pretty nice normal distribution, and temperature follows a pretty close to normal distribution as well. So here I had that same data set, but I was looking at June temperature, and I know that it's normally distributed. So think about the variable we're looking at is June temperature. It's got a mean of 70.75 and a variance of 6.3. That's what we're given. And we want to find the probability that we see this June's temperature be 71.4 or greater. So always helps kind of draw these things out to limit where this probability would be. So I'm looking here, right? That probability has to be less than what value? 0.5, because the area to the left and the right of the mean is 0.5. So if the area to the right of the mean is 0.5, I want something smaller than that. So the process that we're going to use is I'm first going to turn this value of 71.4 into a z-score. Once I have that z-score, I can use that standard normal distribution table. Okay. Now, if I'm thinking about the sign of this z-score, what's the sign of my z-score going to be? So if you remember, the z-score tells us the number of standard deviations away from the mean that our x value is. Okay. So if I see a value above the mean, my z-score is going to be positive or negative. Positive? Yeah, it's going to be a certain number of standard deviations above the mean. Or if we recall that equation that we have for the z-score, we just took our x value, subtracted the mean, divided by the standard deviation. Okay? So anything that's above the mean is going to have a positive z-score. If we were to turn the z-score into a mean, the mean into a z-score, what would the mean have a z-score of? How many standard deviations away from the mean would the value of the mean be? It's 0 standard deviations away, right? It is the mean. Okay? So my next step is to kind of turn this into these. But one thing I often try to do if I'm working through these or just thinking about them is my standard deviation will just be the square root of the variance, right? So I don't know, this is approximately 2.5. Anyway, it's not exact, but approximately 2.5 if I have to put this in my calculator. So if I just look at how far away is my value from the mean, well, it's not even 1 degree, one unit away from the mean. The standard deviation is 2.5. I'm way less than half of a standard deviation away from that mean. So right away, I should be thinking, we might not be completely familiar yet, but we said, really, it doesn't become too unlikely until we're 2 or 3 standard deviations away. Well, here, we're not even 1 standard deviation away. We're not even half of a standard deviation away. So my z-score should be relatively small. So I go ahead and I plug in my values for x, subtract that mean, and then divide by. Now here, if I don't do the calculation ahead of time, I could, for my standard deviation, just plug in that square root of the variance. I can do it like all in one equation, or I can find it ahead of time and then plug that 2.5 or whatever that ends up exactly being in there for my denominator. If I do this, I think I get 0.26. Might be wrong here, we'll see. Trying to do this from memory. So we've got our z-score is 0.26. Now I probably drew this one really not to scale, right? Because that z-score of 0.26 is really close to my mean z-score of 0. So it's probably, if I was trying to draw this to scale, right, 0.26 is going to be a lot closer to that mean of 0. So it's probably going to be that the probability I'm looking for is a lot closer to 0.5 than it would be to 0. In order for that probability to be 0, I would have to see a z-score of like 3 or higher, right? And my z-score is only 0.26. Okay? So if I'm looking at these answers, well, right away we said it has to be less than 0.5. I can rule these out right away, right? B and C. Those are above 0.5. From there, if I'm going to just take a guess at it, well, that area or the probability of seeing that value higher should be a lot closer to 0.5 than it would be to 0. So if I was guessing, I probably would guess A. We can actually work through it, right? So I've got my z-score of 0.26. Let's just make sure that's what it was. Yeah, 0.259. So here, this kind of shows a problem. If I'm looking at that standard normal table, it only goes to the second decimal point, right? So if I want to find positive 0.259, I can't do that. So whenever I have my z-score, I have to round to the second decimal. So 0.259, we'll use 0.26. So I go down here, 0.26, right? It was my second decimal. So 0.6026. But remember, the table always tells us the cumulative probability. Cumulative means it goes all the way back to the lowest value. So when I looked up a z-score of 0.26, the table was telling me the area to the left. I wanted the area to the right, so what's the kind of added step that I have to do now? Simply, yeah, right? The area under the curve is 1, then this area plus this area would have to add up to 1. So I can subtract the area to the left from 1, and that would give me the area to the right. So that's what, 0.3974. Any questions on that? Yeah.
Just for argument's sake, if you were to just do negative 0.26 or like in any sort of concept where it's a greater than, you just want to go ahead and do the negative option of it, is there ever going to be a time where that won't be the correct answer? Seeing that it's symmetrical.
I want to make sure. I think that should always work. I'm trying to think of a situation. If you wanted to find, so that works if you're just looking for the probability being greater than a certain value. If you ever start to get where you're looking for the probability being between two values, you can do a similar thing, but I think what you said technically wouldn't be correct because you could use the other side of it. You would still have to like subtract one from the other. But if you want the probability being greater than a certain value, yeah, right? If I've got a symmetric distribution, once I find that z-score of 0.26, the area to the right of 0.26 would be the exact same as the area to the left of negative 0.26. Yep. So yeah, if that's easier for you to remember, then by all means, just look up the negative z-score. The only tricky part is you have to remember it's only when the probability being greater than. If you have to, if you draw it out, it's pretty easy to just see, oh yeah, I have to subtract that from 1. Any other questions? That's a good question. And we can, and you know, I like that. If I'm doing it, that's probably how I do it, right? Because you can do a little bit quicker as long as you can remember that. You kind of exploit this fact that it's a symmetric distribution. Any other questions? So I have one in here. I don't think we'll start out quite yet kind of using the iClicker. But it's really a very similar example. I'll just point out a couple things with this one, how it's a little bit different. So here I've got February's temperature, right? And I still want the probability being greater than a certain value. Okay? So right away, if we look at these values, I wouldn't actually have to work through this problem if I did ask you this as an iClicker question, because I've got this normally distributed variable that has a mean of what? 28.89 and a variance of 26.16. So if I'm thinking about the standard deviation here, it'd be the square root of my variance. And I don't know exactly what that is, but whoops, it's going to be approximately 5, right? Because the square root of 25 would be 5. So it's a little bit higher than 5, but at least gives us an idea to think about kind of how many standard deviations away the value we're interested in is, right? So if I'm looking at 42.85, and I want the probability being greater than that value, right away I know that has to be less than what? Yeah, the area to the right of the mean is 0.5. I want something much smaller than that. So right away, I can rule out everything except for B. So we know B is the answer, but how could we actually look it up if I gave you some other values that were less than 0.5? Okay. Well, if I'm just looking at this, about how many standard deviations away from the mean am I? If I do some really bad rounding, I'm about 20 away, not 20, about 10 away, a little bit more than 10, right? Standard deviation is a little higher. So I'm going to be somewhere above 2 standard deviations away. So once I start seeing z-scores as high as, and we'll just say for now, approximately 2. I'm going to be way off because I'm just rounding pretty bad here, right? Probably seeing something 2 standard deviations away or even higher is going to be really close to 0. And we end up seeing it's in fact 0.0032. Right? But if I actually go ahead and calculate the z-score, I don't have to just kind of eyeball it. Take that value I'm interested in, subtract the mean, divide by my standard deviation, so the square root of 26.16, I think I get a z-score of 2.73. Right? So we don't have to approximate it anymore. We know that we get this z-score of 2.7. So it's pretty high, pretty far away from that mean. Right? So it should be pretty unlikely that we see a value that high above the mean. Sure enough, if we go to my table, standard normal table, go down to 2.7, and then I think this is, if we go all the way up, that's that 0.03. So scroll down here, 0.9968. So once again, you could do this way, 0.9968. We want the area to the right, so we could subtract it from 1. Or if we wanted to look up negative 2.73, since it's a symmetric distribution, negative 2.73 will give us that same value, 0.0032. Right? The same as if we would have subtracted the area to the left from 1. Okay. Any questions on this before we keep moving? Okay. So if we're okay with that, and I don't know, this was actually the average temperature in Indiana. So if we go back to 2017, the probability that we get, a February that was that warm or even warmer this year, what, 0.32% chance, right? So the average temperature probably isn't going to make it as high this year, but there's still a shot, right? So That was just kind of, I mean, that was just slightly different examples of what we were doing last week, just to kind of refresh our memory. We're now going to kind of move to something where it's really similar, but we're just working in reverse or kind of the inverse, right? So sometimes instead of having this value that we're interested in finding the probability of, we might know that we want the probability of seeing a certain value or less to be 0.9 or 0.7. Right? So we'll kind of give you a setup of what this would look like. So let's say, I don't know, I think the one I use is a test score example. So let's just say, I don't know, we're looking at height, right? And it follows this normal distribution. There is some value for the mean, and it has some standard deviation. I'm not have to be given those things. So I might then be interested, okay, what value for height would kind of be the cutoff for the 90th percent, right? 90th percentile, or said differently, right? That there's a probability of 0.9 that I see a height below this value if I'm choosing a percent range. So what that would be, right? Intuitively, we know, like, well, obviously it wouldn't be like probably 4'11" or 5'2". It's probably something that's a little bit higher. But what's the exact value? Well, if we know that we want the probability we see something below that is 0.9, essentially we know the cumulative probability. So if I think about down here with my standard normal distribution, if I could turn this into a z-score, it should be the z-score that gives me an area of 0.9 to the left. Or what I'm really looking for is the number of standard deviations above the mean I would need to be, such that the probability of seeing something below that would be 0.9. So I now know the probability. Like before, we had the x value and we went and we found the probability x was less than or equal to that value. Now we know the probability x is less than a certain value is 0.9, and we want to back out what that value actually is. Now I'm just using 50, we'll put a number in here. I was kind of using as an example. We're basically working in the reverse order. Before we knew the cutoff value for x and we were finding the probability. Now we know the probability and we're trying to find what that cutoff value for x is. Okay. So try to keep this going in here. I can look that area of 0.9 up in the middle of the table. Right, that standard normal table, my probabilities are in the middle. So the z-score of -3.4, the cumulative probability of the area to the left of that is 0.0012. So if I wanted that area in the tail, I know the z-score that would give that to me is -3.4. If I want 0.9, I'll go down here. I'm kind of hunting around what value is closest. Well, it looks like these are the closest values I can find at 0.9, right? We're constricted to 2 decimals. I'll show you in a second how we do this in Excel. We're not constrained to 2 decimals. But if I'm doing this by hand and using this table so I don't have to do the integration myself, I'm in between these two, right? It's as close as I can get. So the z-score that has a cumulative probability that is 0.9 is 1.2, so somewhere in between 1.28 and 1.29, right? I know that 1.28 or 1.29 would be the z-score that gets me the closest, right? But the actual z-score that gives me exactly 0.9 is somewhere in between 1.28 and 1.29. So in practice, what we'll do is whenever we want a probability or an area to the left, or cumulative probability of seeing this z-score or lower, all different ways of saying the same thing, I know that the z-score is going to be somewhere in between 1.28 and 1.29. Anytime we're in between 2 values, I'll just take the higher of the 2. When I say higher, like the greater in absolute value. So if we're dealing with negative values, and this was like, I was somewhere in between -1.28 and -1.29, I'll kind of ignore the negative sign, take the one that's greater in magnitude. With positive values, it's easy because the higher value is the one that's actually greater in magnitude. With negative values, it's a little bit trickier because the larger magnitude is actually -1.29, but it's less, right? Because we're looking at negative values. So just think about take the absolute value of the two and take the one that's higher. So we just found that this is going to be, so here we'll use 1.29. That's the z value. Well, if I look at my z-score equation, I just found the z-score that would give me the probability of 0.9, or the area in the left to be 0.9. I'll be told my mean, and I'll be told my standard deviation. I could do a little bit of algebra, rearrange this, and solve for what that cutoff value for x would be. That would be 1.29 standard deviations above the mean, which means I know then that the area to the left of that would be 0.9. If I see a cutoff value 1.29 standard deviations above the mean, I know the probability of seeing that value or anything less is always going to be 0.9. Because every time I go to this table and I look up a z-score of 1.29, I'm always going to see well, here is 0.9015, right? But as close as I can get to 0.9. Okay. So another thing that we can do is instead of plugging the values in and then rearranging, is we can just rearrange this and then plug the values in. So when we rearrange this equation, so I do a little bit of algebra here, I get that to solve for that cutoff value, I'll take the mean and add that to my z-score that corresponds to whatever area I want in that left tail times my standard deviation. So what we'll call this is my inverse transformation formula. Right? So I can use this formula when I'm working in reverse, when I know the probability or the area that I want in that left tail, and I'm trying to find what the actual cutoff score that would give me that area would be. Okay. Any questions on that? We'll put some actual values to it here. So let's say I have this test score, excuse me, and I want to know what's the, I gave this exam, what's the score that would be greater than 90% of the other test scores? Or said differently, what test score would kind of be worse than 10% of the other test scores? Or what's that 90th percent cutoff? So here I said, what's the score that will be in the top 10%, right? It's that kind of cutoff for the top 10% or better than 90% of the other scores. Well, here's my original variable I'm looking at, which is the test score. I've got a mean of 72. My variance is 64. So if I take the square root of the variance, that gives me my standard deviation of 8. If I want the value for the test score, that is the cutoff for being in the top 10% or better than 90% of the others, I know the area that I want in that lower left tail. Okay. So if I'm working in reverse here, I know that I want to find the z-score that gives me 0.9 in that lower left tail. Well, we actually already looked that up. That's kind of leading us into this example. But if we go to that standard normal table, look for the probability closest to 0.9 in the middle there, and then go over to find that corresponding z-score, we found 1.29. Well, once I have that z-score, if I go back to my equation, I now have the z-score. I was told the mean, told the standard deviation. It's a matter of plugging those values in. So I looked that up. I find it was 1.29. Now it's a matter of plugging those values into that inverse transformation formula. And I find the cutoff exam score for the 90th percent for this particular example would have been 82.34. So if you're ever in a class and you want to know, well, what was, what score would have been kind of the 90th percent, as long as the professor gives you the mean and the variance or the standard deviation on that test, you could actually back out kind of what these different cutoffs are. So when you're talking about percentiles a long time ago, that was when we only had like a small discrete data set. Here, we're thinking about, we have this kind of nice continuous distribution, okay? So we can find the different cutoffs using kind of this method. Okay? Any questions on this? Okay. So if I ask you to do this, hopefully you should be able to. So I kind of try to work through this one. You might be able to rule some answers out and figure out what it would be pretty quickly. But I want you to try to get used to using that table. Now we're going to be using that table to work in reverse. Okay. So you've got the same setup. It's just now you want to know what's the test score that would be the cutoff for that bottom 40%. Right? I think the wording here is actually wrong because I copied and pasted it wrong. So let me, if you really want this to line up, I guess, what's the highest score that would be the cutoff for that bottom 40%? An easier way to think about it is you're just looking for what's that test score that gives you 0.4 in that lower left tail. Okay. So you know the probability. You want to use that table to figure out what the corresponding z-score is, and then use that inverse transformation formula, which I'll write up here and move out of the way. So once you have that z-score, you should be able to use that inverse transformation formula to come up with what's that test score that is the cutoff for that bottom 40%. Okay. Just give you a little bit of time, kind of work on that, talk to people around you, try to kind of work through this entire thing, make sure you can find the correct z-score using that table, and then we'll talk about it here in a couple minutes. So you haven't gotten an answer in. Take your best guess here. I counted 25 or so. So we'll give it. Everybody got an answer in? 24 of us. All right, I'm going to close it out. 25. Close it out. This really is alarming. We don't have as many people here, but I guess that's on there. So I'll end up giving everybody credit for this. I just wanted to kind of see the recorded responses and see exactly how, like, what percent of us are going to understand this. So don't worry, everybody get full credit for being here. Yeah. So it's the exact same setup we had before. It's now the area we're interested in is 0.4 instead of 0.9. So got my mean 72, my standard deviation, we have recorded as 8. Now I want the cutoff. It gives me 0.4 in this lower left tail. So right away, before I even get too far into the weeds into this, what's going to be true about this score? Well, the z-score that I find, the z-score will be negative, right? But the actual cutoff value for the test score, that's in the, gives me that bottom 40% cutoff, what would 72 give me the cutoff for?
Your score is gonna be-
It's going to be below the mean, right? This score has to be something below the mean because I know that if the cutoff, if I was looking at the test score of 72, that would be the cutoff for the 50th percent, right? Because I know the mean exactly splits this distribution in half. So if I want the cutoff score for 40%, right, or that probably a 0.4, well, it has to be a test score that's less than the mean. Kind of in the other example, we could have said, well, if I wanted the 90th%, I know I have to have a cutoff score that's something above the mean. So I look at these values, 74 is actually above the mean, so I can rule that one out right away. If I'm thinking about test scores, A and C don't make a whole lot of sense at all here. Right? Now, if you're thinking about the z-score, I guess maybe this is a little tricky in that we're thinking about the variable we're interested in is test scores. If it helps, maybe it's that test scores, if this was like height or income or something else, we're looking for the cutoff height. Well, here we have exam score, so we're looking for the cutoff exam score. So what would the z-score that gives us 0.4 in that lower left tail be? So we go to our standard normal tables. We know that we want 0.4 in that lower left tail. So I'm going to look for the closest probability I can find. Looks like in between these two. So negative 0.2, and it's in between these two columns. So we'll go all the way up. In between negative 2.5 and negative 2.6. Like I said, when we have negative values, it's a little bit trickier, but the greater in absolute value, or the larger magnitude there, between negative 0.25 and negative 0.26 would be negative 0.26. So negative 0.26 is the z-score that gives us that cumulative probability, or that area in the left tail that we wanted of 0.4. From here, it's just a matter of plugging everything into that inverse transformation formula. Right? So we'll take our mean, which was 72, add to that our z-score. Now the z-score we found is negative, so we have to remember I can't ignore that negative sign. So I plug in that negative 0.26 there, and then multiply that by my standard deviation of 8. If I do that, I think that's where I get like 68 or 69 point something. Any questions on this process?
So for the previous one, it asked about the 10%, but we subtracted and we got 90%. That's what we used for our z-score. So how do you know when to use the percent given or subtract the one from 100%?
I mean, we have to stop and think just about kind of what that means in English, right? So the cutoff score for the top 10%, that's telling you that you want the area to the right to be 0.1. Here, if I want the cutoff for the bottom 40%, that's telling me the area to the left is 0.4, right? You know, usually we're doing this inverse transformation idea. We're probably more often than not phrasing it as like, what's the cutoff for the bottom 33 or the bottom 60% or the bottom, you know. But occasionally, like especially in the test score example, a lot of times people will phrase things as, well, what's the cutoff for the top 10%, right? What would that cutoff be that would give me the top score, or the probably the right of 0.1? Yeah, so whether or not you subtract that from 1, it's a little bit more just about how we speak in English, right? Like how it would be phrased in English. Now, when it comes like the exam and things like that, I would more often than not phrase it as like the bottom 40%, or what's the cutoff for being above 90% of the other test scores, right? Kind of really trying to make it clear. Does that?
Yeah.
Any other questions? So it shouldn't be too bad. we're gonna. What do I want to do? What order do I want to do? I want to show you a little bit in Excel. I'll show you that in Excel first because it shouldn't take too long. So I'm going to open up that Indiana weather data file that we had looked at last week. And I'm going to click on this worksheet, which is the inverse transformation. Okay. So let's say the area that I wanted in my lower left tail, we'll go back to that very first example with this test scores of 0.9. Okay. So I have my mean, I have my variance. I'm going to delete these and kind of show you what I was doing there. I just kind of recreate it, but kind of walk you through it. So the area I wanted in that left tail was 0.9. That was our first example. So if I'm working in reverse, just like last week, we had the norm.s.dist. I told it a probability. It looked up a z value in Excel. Norm.dist, I told it all the things that it needed to calculate the z-score. It then looked that z-score up and returned to me the probability. So maybe to keep these straight, one thing that might be helpful is, I'll erase the older example first. So let's say I'm thinking about all these different functions I have in Excel. So the ones that we walked through last week would be norm.s.dist. So notice I tell it a z-score, and it's essentially going to tell me the probability. I see a z-score below that value. Norm.dist, that's where I told it all the things it needed to calculate the z-score, which included whatever my cutoff is, the mean, the standard deviation, and then we just had to tell it it's always going to be cumulative. And that did all the intermediate work for me and told me the probability I saw that X value or anything less. So we could use this and kind of what we kind of worked through last class. It makes a little bit more work, but we can at least see the intermediate z-score. Here, it does all the work behind the scenes for us. Well, now we're working in reverse, right? Because now I know the probabilities and I want to find the z-score and then the original kind of variable, the cutoff score for the original variable. I want Excel to tell me that. So now what we're going to do is use, well, first we'll use norm.inv. We're going to tell it the probability that we want, or that cumulative probability, the area in the left tail, and it's going to spit out at us the z-score that gives us that desired probability. We could also do norm.s.inv. Here, we'll tell it the mean. No, I got the order wrong. We'll tell it the probability we want, the mean, and the standard deviation. So it will then find that z-score and then use it along with the mean and the standard deviation, plug it into the inverse transformation formula for us, and give us that cutoff value for X. So we'll kind of look at how we use both of these. So the first one is the one that does all the work behind the scenes for us. And then I'll kind of break it down and show you kind of what it's doing. So norm.inv, right? That's going to be the one. I flipped this, hold on. I wrote these backwards. Norm.inv. And this one up here should have been norm.s.inv, sorry. So norm.inv, well, the area we want in the left tail, or that probability, that cumulative probability we wanted, was 0.9. Comma, tell it the mean, comma, tell it the standard deviation. It's going to look that 0.9 up in the table. It finds that the z-score was about 1.29. It's going to use that z-score of 1.29 along with the mean and the variance to then plug all those values in the inverse transformation formula to then figure out what that cutoff score for the original X variable or the original exam score, right, would be, such that it would be better than 90% of the other scores. So, oh, what did I do here? Oh, I did something wrong here. So 153 on the test score would probably be a little bit higher than 90%. Notice here, I'm not supposed to tell it the variance. I actually have to tell it the standard deviation. So I could calculate this ahead of time in a different cell and just reference that cell, or I could use this SQRT function, which just takes the square root of my variance for me, which that should be equal to my standard deviation. Okay. Notice here what I have up here on the board, I have to tell it my standard deviation, not my variance. Now I should get the exact score we found earlier, which is 82.26 or 25. Now, I think when we did it by hand, we actually found 82.26, but that's because, remember, we had to round our z-score to the second decimal, right? We couldn't find exactly 0.9 in the table, right? We had to get just kind of close. And so Excel can be more precise, right? Excel can find the z-score that exactly gives me 0.9, okay? So we can be a little bit more precise if we're doing this in Excel. Any questions on that before we keep moving? So let's say I instead try to break this down to mimic what we did by hand. So instead of using the table, right, to find the z-score from the desired probability I had, I can do in Excel that exact same thing, but instead of using a physical table, I can use this norm.s.i_v function. I'll tell it that cumulative probability I want, or the area in that left tail, and it's going to tell me the z-score that would give that to me. Now, we know from earlier it should be between 1.28 and 1.29. And sure enough, Excel can find the exact z-score. Doesn't have to put it within this range, right? So the z-score that gives me exactly 0.9 is the cumulative probability, 1.2815. Well, now that I have that z-score, I know the mean, I know the variance, I could just do the math, have Excel do the math for me, which is take my mean, add to that the relevant z-score that's associated with the probability or the cumulative probability I want, and then multiply that by the standard deviation, which here, that would be the square root of my variance. So this should do the exact same thing that the norm.inv function did. I just get to see the kind of intermediate step, right? Sure enough, I get the exact same value. Okay. So we can work in either direction by hand. We can work in either direction in Excel. And if I've referenced everything like I have here, one thing that's kind of nice is, well, I could change this to look at the bottom 40%. We should find that same value that we found. Now it's a little bit more precise. I think when we've looked at it was 69.98. It's actually a little bit closer to 69.97 if we don't have to do all that rounding. But yeah, really reproduces the same thing that we did by hand. Okay. Any questions over anything there in Excel? We're okay with that? All right, so I'll save this for the end. I'll show you this kind of at the end here. I'm going to, so a little bit of kind of reminders here. It has some different values. The inverse one matches up, but we could kind of go back to what we were doing last class. And here's the norm.dist function as well that we were using. The next thing we're going to talk about starts to go into the next topic, which is sampling. Before we do that, I want to show you something that I've mentioned in the past, but I didn't really give you a reason, or I should say a reason. I didn't really show you exactly why it's true. So at one point, I told you that if we went one standard deviation above and below the mean, that the area in between that value, those two values, would always be 0.683. I think if I remember the third decimal correctly, I might be a little bit off. We'll see once we work through this. So if I'm looking at my original variable, if I go one standard deviation below the mean and one standard deviation above the mean, the probability I see something in that range, 0.683, always. So we can start to think about why that has to be true. Okay. So one way of looking at this is, if I were to turn these two values into z-scores, what would they have z-scores at? Yeah, someone's holding up their finger, right? And one standard deviation below the mean and one standard deviation above. Well, that's literally the definition of my z-score. So I'm z-score of -1, I'm one standard deviation below the mean. Z-score of 1, I'm one standard deviation above the mean. Okay, we're all on board with that? So if I go to my table and I look up that z-score of negative 1.00, if I look that up, I can find that area to the left here. If I look up that z-score of 1.00, I can find the cumulative probability of seeing a z-score of 1 or anything below that. So if we go and do that, because I could probably guess and get pretty close to the numbers, but we could actually look them up here. Negative 0.1587 is the area to the left of a z-score of -1. And then 0.8413 was the probability of seeing a z-score of 1 or anything. So we got 0.1587, 0.8413. If I want the probability of seeing something in between those two z-scores, what would I do here? Yeah, right. If I know this entire area is 0.84 and this area is 0.15, if I subtract this out from the larger area, I'll be left with just what's in between. Right? I'm going to take this and subtract it from the larger one. So 0.8413 minus 0.1587 should give me, I'm doing this, 6, 8, 2, 6, if I'm doing math in my head correctly. So I rounded it, right? When I told you it in class, whatever, I don't even know if it was last week, might have been right before that, right? It's always going to be 0.68. It doesn't matter what these values are, as long as the values correspond to being 1 standard deviation above and 1 standard deviation below, the area in between them, and the probability I see something in between that range, will always be that 0.68 or 68%. Any questions on this? And I could recreate this and use a table to show you the other values, which I think was if I go 2 standard deviations above and below, it's like 95%, 3 standard deviations above and below is like 99.7. I'd use the exact same process to kind of prove to myself that those are in fact the right numbers or the right probabilities. There's another way we can think about this as well. And this one kind of exploits some other things about the normal distribution. So what if I was using like the inverse approach here? So let's say I told you that if I go 1 standard deviation above and below, right, probability here was 0.683. Another way I could prove this to myself is if the probability in between these two values is 0.683, what's the probability I see something more than a standard deviation away, right, in either direction? So what's the kind of probability that I see something in these tails? It would just be the area under the curve is 1. Yeah, right. I just subtract that from 1, right? So I've got what, 0.317 approximately. Well, that's the total area of the tails. So how much would be in each tail? Well, if this is a symmetric distribution around the mean, they should have the exact same area. So I divide that by 2. You get what, 0.15, no, 0.158 or something like that. 585. There we go. So I just divided that by 2. So I know the area down here is 0.1585. Well, I can find the corresponding z-score that gives me 0.1585 in that lower left tail. Now, if I look this up using the inverse, so I look for the probability that's closest to 0.1585, hopefully I find a z-score of -1, right? So I go up here, 0.15. Oh, did I do math wrong? Oh, well, we rounded it to the 3rd decimal here. So if I kept all 4 decimals, I would get actually, sorry, 0.1587. Right? It's going to be a little bit off because I rounded to the 4th decimal here. But sure enough, when I find that probability that's closest to 0.1587, it's right here, -1.00. So I can do this either way, right? I could prove it to myself using kind of what we were doing before or using this inverse method. If I go one standard deviation above and below the mean, I'll always have a probability of seeing something one standard deviation above and below the mean will always, that probably will always be 0.6826 or whatever it ends up being. Okay. Any questions on that before we keep moving? All right. So shouldn't be too bad. So we'll kind of introduce the next topic here. So we're not going to probably do any computation for the rest of the class. So we can all take it easy, right? But we're going to start to talk about kind of the broader picture behind what we're doing. And I think this is a part of statistics I enjoy. I don't like computation. It's not interesting at all to me, but the interpretation and kind of thinking about some pitfalls that might exist, that's what to me is interesting. So we talked about before that we often want population data, but we don't have, we have to take a sample, right? There's things that can go wrong in that sampling. So first of all, we might have a finite or infinite population. More often than not, what we're dealing with, there's going to be some number we can put in the population, right? It's going to be finite, even if that number is, however many people are in the, the world right now, right? So even if it's in the billions, we can still cap it, right? We still have a finite population. So more often than not, that's how we're going to be dealing with. And it really doesn't matter a whole lot for the sake of what we're doing in this class. If you were to kind of continue to take more advanced statistics, we'd have some differences in how we treat finite and infinite populations. But for the sake of what we're going to do, it doesn't largely matter. So this is why I said I'm going to go through some of this stuff quickly. So it's not feasible to get population data, right? We talked about a census is expensive, just the time that it takes, maybe the data won't even be relevant anymore. And so we're going to take a sample. Once we take this sample, we can calculate things like the mean, right? So I'll have them, maybe I'm interested in income, right? So I take a sample of 100 people, I calculate the average income. I can then use that mean from the sample to make inferences about the population mean, right? Where I think the if I take a sample of 100 people and I see the average income or the mean income is 55,000, well, I can probably rule out that the true population mean is 120,000, right? I know my sample might be a little bit off, but probably not that far, right? So that's kind of the idea behind what we're doing. We're going to use these sample means to make inferences about the population. Now, we've already kind of talked about this, but our population is of size capital N. We'll kind of start calling our sample size this lowercase n. That's the size of our sample data. So what should be true is that if I'm randomly sampling from my population, if we think about the income example, every individual should have a 1 over capital N kind of chance of being selected, right? So everyone should have the same probability of being selected, right? It shouldn't be that some certain people are more likely, because if I was more likely to be selecting wealthier individuals, well, then I know my sample is going to be skewed, right? I need it to be completely random so that when I start randomly picking people, I make sure they're from all over the income distribution, not just like one side. So we can do this with or without replacement. Doing it with replacement would be the idea if I put all the names in a hat, I draw out a name, write that person's income down, put it back in the hat, shuffle it up, draw another name, write that person's income down, kind of continue through that process. That would be with replacement. So that isn't probably a huge issue if I'm dealing with something like the population of the United States. But if I'm maybe interested in, I don't know, what the average age in this class was, I have all your names in a hat, I want to draw 10 of you. So I draw one out, write that person's age down, put it back in, draw another person out, write that age down. What's a problem that could happen if I do with replacement? I get the same person, even if I only get them twice, right? Well, now they're counting for 2 out of the 10 observations, while everybody else would only be 1 out of the 10, right? So that one person, like I'd be overweighting their age. Why? Right? There's no reason. So with replacement, I mean, more often than not is not appropriate, right? More often than not, and I say here that it's better, we should always be doing this without replacement. Once I get someone's name, I should kind of I can't draw them again, right? Now, like I said, I'm not as familiar with contexts where replacement is good. I think when it comes to things like in the medical field, there's some situations where with replacement they can justify, but for the most 99% of the cases you look at, you don't want to do it with replacement, right? So probably doing it without replacement is almost always going to be better. We can skip this because we're not going to deal too much with infinite populations, but I do want to get to the next thing, which is, okay, I've got this sample. Maybe I selected 100 people at random, right? The problem is, if I'm interested in something like income, right? And what the average income of the United States is, well, what if I was doing my random sampling around or in a town that has a university? I'd probably be over selecting kind of college students. So my sample of 100 people, maybe 50 of them end up being college students, right? What do you think is probably true about a college student's income relative to the average person in the United States? It's probably a little bit lower, right? So my sample mean, I almost have built in that it's going to be lower than what the actual population mean is. So if I ever have a situation where my sample doesn't line up with like the demographics of my population, well, then I'm going to have a bias built into my sample, right? Biased by whatever I was over selecting, right? In this case, it would be lower because I was over selecting a group that I knew had a lower income kind of relative to the population as a whole. The other example I always kind of give, because I think it's just easy to think about, is height. Say I was interested in the average height, and I take a random sample, and I just so happen to end up with 60 males and 40 females. What's probably true about my sample mean relative to the population? I've got 60 males, 40 females, and I'm looking at the mean height. Probably a little bit higher than what the average population mean would be. Or sorry, what the population mean of height would be for the US as a whole. Because, I mean, this varies slightly. I'm sure maybe there's one country where you could tell me like 60-40 lines up. But on average, right, for the most part, most countries have about a 50-50 breakdown. It might skew a little bit one way or the other, but for the most part, right, we know that in the US, at any given time, it's about 50% male, 50% female. And so if I'm looking at my sample, I want to make sure that my sample lines up with the US as a whole. So if I want my sample size to be 100, and I'm interested in height, what I might want to do is say, all right, I'm going to randomly sample 50 men, randomly sample 50 women, then kind of throw those together to get my full sample size 100, and it's still random, but I've ensured that my demographics in terms of gender match up with what I know kind of the population of the US looks like, or at least as close as I can. So this is the idea of stratified random sampling, right? I'll break my population down into these groups where I don't have an overlap. So a lot of times, use a general one, we might do age categories, right? Maybe if I wanted a sample size 100, I take randomly sample 10 people between 10 and 20, 10 people between 20 and 30, so on and so forth. And I would have 10 groups, each of kind of random 10 people, throw them together, and I'd have my full sample of 100. That way I can ensure I have a fully random sample, but I've made sure that each age bracket is like equally represented, or that it matches up with the distribution in the US. So probably in practice, I think, as we get to the older ages, people attrition out of the population or they die. So, if we look at older age brackets, maybe they all shouldn't have 10, maybe 10 to 20 should have 10, 20 to 30 should have 10. But once we get to like 60 to 70, maybe I only want like 7 or 8 random people from there, right? So I can make sure that the proportion of each age group in my sample matches the population. Otherwise, I know that my sample mean is going to be biased. So we divide up into these non-overlapping groups. We randomly select from each one of those groups and throw them all together, get my full sample. A lot of times where we see this is things like, here we go, age, gender, sometimes income. We want to make sure that the income distribution of my sample looks similar to the population. Really, anytime where I know there's a characteristic that's related to my variable. So that's why I kind of always go to the gender height example. You could go to age, income, right? Anytime the variable I'm interested in is influenced by a characteristic, I want to make sure that that characteristic in my sample matches that of the population. Any questions on just this general idea? So cluster random sampling is a very similar idea. It's just that instead of breaking the population down into non-overlapping groups, right? We're just going to look at smaller scale versions of the population. So this might be something like, if I'm a big company and I want to gather some data kind of quickly, and I just want to put together a sample of 50 people, and I'm located in 5 cities, but I'm still interested about the US population as a whole. Well, maybe for me, it's a lot more feasible to just randomly select 10 people from each one of those 5 cities, throw them together to get my sample of size 50, and then I can use that sample mean to start making inferences about the population. So with cluster random sampling, it wasn't that like the characteristics across cities weren't overlapping, right? So sorry, with stratified random sampling, I was looking at non-overlapping groups. With cluster, they can still overlap, right? So it's more like I have like a smaller scale version of the population. That would be like, just looking within one city, right? So often cluster random sampling, it's the same idea, but we often do it with respect to geographic areas. Right? Another place we could see this is, let's think about, so if I'm looking at state, or if I'm looking at, if I'm looking at like political polling data, right? I may want to make sure that each state is kind of equally represented, right? Especially if it's something where I think the voting is going to happen by senators, because we know that each state gets the same amount of senators, right? So maybe I want to make sure that if I want a sample of size 100, I randomly sample 2 people from each state kind of being a smaller representation, a smaller scale version of my population. So randomly select 2 people from each state, throw them all together. I'll have a random sample size of 100, where each state kind of has equal representation. That would be cluster random sampling. Okay? Now, probably wouldn't want to do that in most cases. In most cases, if I don't want every state equally represented, I would probably want to do something like make sure my sample, kind of the proportion of people in my sample from California matches that of the portion of people in the US who are from California. So I'd probably be selecting like 50 people from California, but only like 2 from Delaware, something like that. Kind of really the idea would be like if I was almost choosing people to put in the House of Representatives, that's kind of what we would probably want to add in as well. But it's the same idea as stratified random sampling. It's just we're not basing it off of a characteristic, we're basing it off of usually some type of a geographical area. Questions on the, I'm not gonna necessarily ask you for specific to give you the definition of these, but I'm really trying to set up to make sure we can start thinking about biases that might exist in the samples that we're going to look at. So I kind of already talked through this one, but right, they do this all the time with political polls to make sure that each state is kind of represented in the sample the same proportion as they are in the population. So, we have to do this. We know that these biases might exist. If we don't make sure that our characteristics in our sample line up with the population, there's also some other things that could go wrong as well. So even if I make sure that I do all this random sampling as well as cluster and stratify, maybe I fix all the problems or I get a sample that looks very similar to my population. It could be that the procedure in which I was sampling wasn't actually completely random. Okay? So what could go wrong? So I'll set this up, and I think we'll just get to talk about the biases today, probably revisit them next week on Monday. But we'll use this 1936 presidential election to think about specifically 2 other biases that might exist. So Alf Landon was running against FDR in 1936. FDR, well, hopefully we all know, was president of the United States. I'd never heard of this guy in the history classes I took, but what a great name. But he lost, right? So if we go back to 1936, there's this thing, my grandma used to get these when I was a kid still. They're like magazines, but literally digest that they would send them out. It was kind of like a magazine. And they thought they had this brilliant idea that they could predict the election before it even happened. All right, so they had this huge scale operation. They mailed out 10 million survey cards. Right? 2.5 million people responded. I don't know what classes you guys have taken, if anyone's done anything with like survey construction. If you can get a 25% response rate to the mailer, you're doing really well, right? So this was really good news. They look at this like, man, we have a sample of 2.5 million people. That's a huge sample. We should be able to accurately predict what which way the country's leaning. So they predicted that Alf Landon was going to win in a landslide. 57% of the popular vote, the electoral vote was going to be skewed pretty heavily towards him. Now, obviously, we know that that didn't happen, right? FDR won. So not only did they predict it in the wrong way, and they predicted a landslide in the wrong way, but Roosevelt actually won in a landslide. Right? I mean, not a history buff. My guess is this has to rank up there as some of the most electoral votes anyone's ever won, 523. Okay? So how'd they get it wrong, right? I've got a bunch of stupid things up here like math errors. They use the samples as a population variance equation. But then you get some actual interesting questions. Well, what if I only sent the mailers to Republicans? Right? And this is like the extreme, but maybe not just only sent it to Republicans, but maybe I accidentally oversent them to Republicans. So when I sent these out, maybe 7.5 of them went to registered Republicans and only 2.5 went to registered Democrats. If I did that on purpose, I'm done. Right? I should have known I was going to get a wrong prediction. But if something in the process led to this, right, then maybe we want to understand how we could avoid that. So what we would end up calling this is our selection bias. Right? We over-selected from a particular group. The other one could be that, okay, I know I didn't over-select. I sent 5 million to registered Republicans, 5 million to registered Democrats, or maybe not registered, but the idea would be I somehow was able to predict I got this even split, right? Well, if all the Democrats decided not to respond to this mailer and 2.5 million of the Republicans decided to respond, well, now I'm only going to have a sample full of only registered Republicans. So I might have a non-response bias built in. That one group, even though I sent it out equally, I eliminated my selection bias. For some reason, one group just didn't want to respond. Okay? So these are kind of our two biases that exist, right? Our selection bias and our non-response bias. Okay? So selection bias, if we're over-selecting from a certain group, so the idea here is over-selecting Republicans. Non-response bias is one of those groups just doesn't respond at as high of a rate as the other. Both of them will just lead to a sample that has one group overrepresented relative to what they make up of the population. So we can kind of go back and think about this specific case. So what they did when they sent these mailers out was they had all phone books, like they had all these phone books, and they had each state's, here it's the BMV, like in Michigan, it's the Secretary of State, but basically whoever was issuing car registrations in that state. To make sure that they were actual people, like maybe the name in the telephone book or the car registration wasn't real, they cross-referenced them. So the only way you got a mailer is if your name was both in a telephone book and in one of these, state's car registrations. Okay? So what problem is going to exist if I only sent my mailers to people who have a phone and have a car in 1936? I'm only getting rich people, not just wealthier individuals, but back in 1936, to have your own telephone number meant you had your own telephone line, which meant you probably didn't live a couple miles out of town, right? These rural areas wouldn't be represented here either. So my sample is going to be overpopulated with kind of wealthier individuals, but maybe also a little bit more kind of urban or kind of suburban type individuals, which wealthier people on average, not everyone, tend to vote a little bit more Republican. Okay? So right away, I'm going to have this selection bias. I over-selected Republicans by using this process. Okay? As far as the non-response bias, I have no reason to believe that maybe Republicans or Democrats respond at different rates, and there's really not much I can do about that ahead of time. Someone went back, they found a bunch of individuals who were voting in the 1936 election, what their car and telephone status was at the time, and then how they actually voted in that election. So this was the survey, but someone it was like 15, 20 years ago, went back and found all these old individuals who were actually alive at the time and kind of asked them what group they would have belonged to in terms of car and telephone ownership, and then who they actually voted for. So what they found was pretty interesting. So people at the time who owned a car and telephone, about 52% of them reported that they ended up voting for land. So this was the group that really was in that Literary Digest poll. So of course, that was actually a pretty good prediction. They actually predicted it correctly for people who owned a car and telephone. But even if the Literary Digest wouldn't have done this cross list, if they just would have used like any name that was in either of these, notice people who only owned a car but didn't have a telephone. This is probably wealthy people who don't live out in the country. Even for them, 60% ended up voting for FDR. And people who only own a telephone, 62% voted for it. If you had neither, these are poor individuals, the vast majority of them all voted for FDR. So because I selected only people from this group in how it was sampling, I had this huge selection bias built in. Right? So that's kind of a good look into why my selection bias matters. And this I can really only do like ad hoc, so like looking backwards. This is kind of a hindsight is 2020 thing. But let's be realistic. The Literary Digest could have probably predicted this ahead of time, that their method was going to oversample this wealthier group who tend to vote more Republican. Questions on this? We'll do one more thing and then we'll kind of end here and we'll pick up on this next class. So if instead only we had 2.5 million Republicans sent it back with 0 Democrats, we also would have had a bias built in, but because of a non-response bias. So what these individuals did is they went back, found those people who actually were able to vote in the 1936 election, and something kind of interesting came out of it. So they had data on this other poll, right, that was just given to everybody in the United States. It was some political poll, this straw ballot, like how they're going to vote. So from this other poll, in that time, they can figure out, well, we're different groups, right? And people who are going to plan, who are voting for either Roosevelt, that they have a different response to these political polls, right? So using this other political poll, what they found was people who owned a car and telephone at the time, in 1936, of the people who ended up voting for Roosevelt, 16 or 17% of them responded to this other political poll. But the people who ended up voting for Landon in 1936, who had a car and telephone, much more likely to return this political poll, right? Almost twice, actually more than twice as likely. So here we've got a non-response bias that's coming from the people who voted for Roosevelt were just less likely to respond to these political polls. And in fact, it doesn't matter what the Literary Digest would have done in every one of these categories, only a car, only a telephone, or owning neither. Notice, in each one, the people who ended up voting for Landon were much more likely to respond to these mailers or these political polls. So how do we deal with this non-response bias? It's very difficult. We can try to use incentives, right? Equally incentives for both groups to try to make sure that everybody is more likely to kind of send it back. But it's really hard for us to fix a problem like this. If Republicans are just more likely to respond to a political survey sent to their house, it's going to be really hard for me to predict anything politically, right? And we'll kind of talk a little bit about this on Monday. We'll revisit this idea of bias, and that will lead us into thinking about the distribution of sample means, okay? So start working on those homeworks before we meet on Monday. Other than that, have a good weekend. I will see you guys next week.